You know, there's a secret hiding inside one of the most famous numbers in all of mathematics. And today, we're going to find it. This is the secret of pi.
Oh yeah, we all know this one, pi. That constant that kicks off with 3.14159 and just keeps on going forever. It's irrational, which is just a fancy way of saying it never ends and never repeats.
And on the surface, its definition seems so simple, right? It's just the ratio of a circle's circumference to its diameter. A perfect, unchanging relationship that's true for every single circle, no matter how big or small.
Okay, but if pi is really just about circles, then this is where our mystery really kicks off. Why does this one number keep showing up in places that have absolutely nothing to do with them? I mean, take a look at this. Why does pi pop up in this Schrödinger equation? That's a cornerstone of quantum mechanics, describing how particles behave like waves. There aren't a little circles inside an atom, yet there's pi right at the heart of it all. And what on earth is it doing here? This is just an infinite sum of fractions, 1 over 1 squared plus 1 over 2 squared, and so on. There's no obvious connection to geometry at all. So why is pi lurking in the answer? Well, let's dig in. Our first case file is a mathematical puzzle that, I kid you not, stumped the greatest minds in the world for almost 100 years. So way back in 1650, a guy named Pietro Mangoli posed what became known as the Basel Problem. He asked for the exact value of that infinite series we just saw. Mathematicians could get close, they could approximate it, but they just couldn't find that one clean, beautiful answer they knew had to be out there. Get this, for 84 years, this problem was just unbreakable. The famous Bernoulli family, we're talking a dynasty of math giants, they all took a crack at it and they all failed. It was one of the most famous unsolved problems of its day. And then along comes this brilliant 28-year-old mathematician, a guy named Leonhard Euler, and he finally cracks it. His solution was so clever, so completely out of left field, that it made him famous almost overnight. And the answer he found? Pi squared divided by 6. Yeah. I mean, if you're sitting there going, where did pi even come from? You are not alone. The connection was a total shock. How could a number defined by a circle be the answer to a problem about adding up a bunch of fractions? All right, on to our next piece of the puzzle. We're jumping from pure math to a simple game of chance. And, well, you can probably guess which number's about to make another surprise appearance. So picture this. It's 1777, and this French nobleman, the Comte de Buffon, he poses a question, and it sounds almost like a party trick. The whole setup is just beautiful in its simplicity. You take a floor with parallel boards, or even just a piece of lined paper. You take a needle and you just toss it on there randomly. Buffon figured out that the probability of that needle landing on a line is directly and very elegantly tied to pi. So yeah, here we are again asking, where's the circle? There are no circles here. It's just straight needles and straight lines. It's a game of pure chance, but the outcome is governed by the circular constant, pi. It's another huge clue that pi is so much more than what we learned in school. Okay, for our last clue, we're going to jump way ahead to the modern computer age and dive into the infinitely complex world of fractals. You're looking at the famous Mandelbrot set. It's this incredible, infinitely complex shape. Basically, a computer takes a number, runs it through a really simple repeating equation, and then colors that number based on how fast the result shoots off to infinity. The black parts are all the numbers that just stay put. So in 1991, a computer scientist is digging around in a very specific spot on the edge of this thing, and he finds that if you pick a point just a tiny bit away from that spot, the number of steps it takes for that point to escape, when you scale it the right way, actually starts spelling out the digits of pi. Okay, let's take a step back. We've got this impossible sum, a game of needles, and a crazy infinite fractal. 3 totally different worlds, and yet pi is the guest of honor in all of them. So, what's the secret? What's the common thread here? Here's the key, the big reveal. We've been thinking about pi all wrong. It's not really about the shape of a circle. It's about what a circle represents. You see, pi is the fundamental constant for anything that is cyclical, anything that repeats or oscillates or rotates. Think about it. Waves, rhythms, the seasons, the swing of a pendulum. The universe is absolutely packed with cycles, and pi is the number that describes their nature. A circle is just the simplest, most perfect picture of a cycle. And this idea, It goes way deeper than just patterns we can see around us. It goes right down to the fundamental operating system of the universe itself.
Today, physicists are starting to see pi as something like a universal quantum signature. It's the constant that acts as a bridge, turning patterns that repeat in space, like a particle's standing wave, into distinct energy levels. It even shows up in equations that describe the energy of empty space, literally structuring the quantum vacuum.
And that brings us to this quote from the researcher Nenda Lumbu-Barak, which just flips the whole thing on its head. It suggests we've had it backwards this entire time. We didn't just cook up pi to describe the circles we saw.
The idea is that the universe itself is fundamentally built on a cyclical, periodic language, and pi is a key letter in that alphabet. It connects geometry, information, quantum fields, the whole cosmos. A circle isn't special because we defined pi from it. A circle is special because it's one of the clearest ways we can actually see this fundamental truth of reality.
So in the end, it turns out pi isn't just about a shape at all. It's a signature of order, a fundamental rhythm woven into the very fabric of reality. Which leaves us with one last, pretty big thought to chew on.